Hello, everyone. Good morning. How's everyone doing? All right. Perfect. All right. Let's welcome Dr. Ron Livne. He'll be talking about PyXL, a chip that runs Python at turbo speeds. Let's give it up for Ron Livne.
Hi, thank you. Just a quick fix. I'm not a doctor, just an engineer. Okay, so thank you all for coming here today. My name is Ron. I'm a software engineer with about 17 or 18 years of experience, ranging from high-performance computing to high-frequency trading, networking, low-level stuff in general, or you can just sum it up like I make things go fast. And today I'd like to share with you, actually for the first time, this is my first PyCon, the first time that I'm showing this project, PyXL or Run PyXL, I'm still playing with the name, which is a chip that is built from the ground up for running Python workloads. So let's get started. So a bit of motivation, I think many of you can relate to this. I was working at a company a couple of years back where we did research and developed machine learning-based algorithms using Python. The problem was that we had almost always encountered performance issues, and we had to reroute the whole thing in C or C++. So I found this kind of process to be kind of tedious and inefficient. So I thought I could maybe try to mitigate it using tools such as PyPy, which does JIT, or Cython that compiles to native C. But each of these tools had their own set of limitations, and it didn't quite match our workflow. So a few years later, I started thinking about why are things the way they are. Now, I don't mean why Python is slow. I think many of us do know why Python is slow, but it's more like, why have we come to a point in time where CPUs are not favorable or don't really support well natively languages such as Python, which are dynamic language in essence. So I found this quote on Wikipedia, which says, by design, C's features cleanly reflect the capabilities of the targeted CPUs. Well, what this actually means is that when C was developed, it was developed in light of the architectures that were readily available back then. And since then, programming languages and CPU architectures kind of evolved alongside each other. And we just converged to where we are today, where we have CPUs that are really, really good at running C, C++, Rust, stuff like that. And we need virtual machines for just about anything else. So today I'd like for us to try and answer the question of what would a CPU look like if we had built it from the ground up just for Python. Okay, could be for any other language, but we'll start with Python. Okay, so before we do, let's start with some numbers, because we all love numbers and results, so we'll start with that. And I'd just like to show you a really simple example here. So you can see here the regular Fibonacci function. This is the recursive function, and it is invoked in the number 14. And if you're wondering, the answer should be 610. Okay, so what we're going to see now is how many cycles it took PyXL to run this specific workload versus how many cycles it took a MacBook Pro with an M1 Pro chip that runs CPython 3.11 to run the same Fibonacci test. And before I show the result, I'd like to pause for a minute and explain why I'm counting cycles and not just measuring row time. So the reason for it being that I'd like to establish which platform is more efficient. And by saying more efficient, what I actually mean is which platform needs to take fewer steps to complete the same task. So the fewer steps that you need to take, the more efficient you are, right? Makes sense. This is kind of reminiscent to something called IPC, which stands for instructions per cycle, which is an industry standard way of measuring CPU efficiency, and it is independent of clock speed. Clock speeds can be played around to a certain extent. So without further ado, So a Mac takes like 134,000 steps to calculate this Fibonacci benchmark. And PyXL takes only 37,000. So as you can see here, PyXL actually takes 3.6 times fewer steps to run the same program than a MacBook Pro. So just to frame things a little bit better, it would be like next-to-use computers would be like 2 or 3 times faster or more power efficient, which kind of never happens, right? So what we can take from here is that PyXL is not just something incremental. This is actually a paradigm shift in the architectural level, okay? Okay, so you could argue that this is just Fibonacci, and you'd be right, this is indeed just Fibonacci. But to that I would say that there are many branchings because you need to establish whether you have reached the base case each time you enter the function. There are many simple arithmetic operations. You need to do the -1, the -2. You need to add both terms together. And there are many stack manipulations. This arises from the fact that CPython is a stack-based machine and not a register-based machine, which means that you need to place your operands on certain places on the stack, and you operate on the stack all of the time. So there are many pushes and pops from the stack. And also there are many function calls and function returns due to the recursion. So what I wanted to show is that PyXL addresses these very known bottlenecks. And I don't know what about you, but I don't know many Python programs or programs in general that don't have if-else ladders and function calls. So I think to a certain extent you can start to extrapolate from here. Okay, so what is run PyXL? And before saying what it is, I'll start with what it is not. So it's not a virtual machine, okay? There's no software here. It's not a JIT compiler, and it's not like I took the CPython virtual machine and rewrote it in Verilog or something. That would not work. It is not fully CPython compliant, and it is not running CPython bytecode directly, okay? What it is an end-to-end solution for running Python in hardware. It has its own custom toolchain, which means a compiler, a linker, and a binary generator. It has its own adapted execution model, which means it does not operate exactly the same as CPython, okay? It has kind of a different MO. And it is working on real hardware. Everything you see here actually works on hardware. This is not simulation of something, okay? So let's talk a bit about the architecture. So as you can see, there are 2 main blocks here. There's a blue one, and there are many purple stuff, okay? So the blue thing is just the host, which is a regular computer where you write your Fibonacci function, for example, okay? And let's say that I want to run this Fibonacci function. So what I would do, I write a Python program. I pass it through the toolchain. The toolchain then generates a binary file, which I can then hand off to a client. The client is just a regular Python software running on the computer. And that would connect to the control CPU, okay? The control CPU resides in this thing called SoC. SoC stands for System on Chip, which means that there is more than just one thing on that chip, okay? So it connects to the control CPU via TCP. There's a TCP server running all the time and waiting for new commands to arrive from the client. And then the control CPU lays out the program onto the shared memory, the program and the data itself, and tells the PyXL CPU to start executing the program. The PyXL CPU then starts executing the program, and once it is done, it notifies back the control CPU that it is done, and the control CPU can return the value back to the client, and we have a result, okay? Okay, now for the tool chain. So again, if it's blue, it's not an inherent part of the PyXL ecosystem. So in this example, there's the dis. This is just the CPython dis module, which compiles Python code into CPython bytecode. So I'm using that. The yellow box that says prog is your program that you want to run. And if you really want to suffer, you can write in assembly, okay, in PyXL assembly. It's not very nice, trust me. Okay, so we take a program and we push it into this module where we get bytecode out of it. The bytecode then goes into the compiler, which creates an object file. This object file now goes into the linker where it waits for the other object files to arrive. Same goes for the assembly, via the assembler, into an object file, into the linker, and now we have a linked object, goes into the binary generator, and now we have a binary file that we can hand off to the client, and we can run it. For the control CPU. So the control CPU, it's kind of simple. It's responsible for loading programs onto the PyXL and telling it to run those programs. It is responsible for I/O in general. More specifically, it does it so in this current implementation via network. And it orchestrates the whole thing, okay? It knows when a program is started, when it is ended. You can ask via the client program to read the memory directly, stuff like that, okay? And there's the PyXL CPU, which is the heart of the system, obviously the most interesting part of the system. And it has the following interesting parts. So it has natural support for dynamic typing, okay, because Python is a dynamic typed language. And we'll see in a few more slides how exactly it works. It has an internal stack module because CPython, again, is a stack-based machine, and there are many, many instructions or specialized instructions that we can have that would make our life much easier and faster, okay? And it is a pipeline CPU. Now, for those of you who do not know what a pipeline CPU is, I'd like to think of it like a shoe factory. So why a shoe factory? So as you can see, there are people in the shoe factory. They're working on creating shoes, okay? And there are many types of shoes. So each type of shoe corresponds to a specific type of an instruction. And each kind of worker corresponds to a specific module within the PyXL processor that can do a certain type of work. Now, what you don't see here is that there's this guy out of the picture that looks at this clock, and every second that goes on in his watch, he places a new shoe onto the conveyor belt. Okay, this is a conveyor belt. It keeps moving all the time. So a worker may say, okay, this is a really special shoe. Please please stop the conveyor belt for a while. But we try not to do it as often, okay? So the most important thing to keep in mind here is that we do not wait for a shoe to fully end production before placing a new one to the conveyor belt, okay? So the analogy here is we're not waiting for an instruction to be fully executed before issuing the next one in line, okay? So that's what a fully pipeline CPU means. So let's see how both systems stack up against each other. CPython against run PyXL. And we'll take something really, really simple here, okay? So we have this add function, which takes x and y and returns x plus y. Really simple stuff, right? And on the right-hand side, you can see the corresponding CPython bytecode, which I'll just explain briefly. So the first one says load fast x, which means take x from wherever it is in memory. I'm not talking about memory management today. And just push it to the top of the stack. Same goes for y. And then the binary op of plus needs to take both terms that reside on the top of the stack, add them both together, and replace them with the result, okay? And then we can return the value. Okay, so we're going to see here a side-by-side comparison of both systems and how they handle this simple add operation. So in the middle, we can see the CPython bytecode that we have seen in the previous slide. Now, I know that I said that PyXL does not run CPython bytecode directly, but I do keep it here for simplicity reasons and because it is kind of representative enough in this case. The orange boxes are the corresponding stacks of both systems. And on the CPython side, we see there's a heap, but for some reason, it is missing on the PyXL side. So not to worry, PyXL does have a heap, but it only uses it when it really needs to. So in this case, when I'm just trying to add 300 and 400 to integers together, I don't really need any heap services. So the execution model is kind of different between PyXL and CPython. So let's get started. So here in the white boxes, it says what each of the systems is going to do in the next step. So both of them say load X and place it on top of the stack. Okay, let's do that. So as you can see on the CPython side, we have X, which points to an object which contains the number 300. Okay? And on the right-hand side, in PyXL, we can see int 300. So it obviously says integer 300, but why do I have to say that this is an integer? So this is a part of the supporting of dynamic types in Python, okay? So what I'm doing, I'm taking the value and I'm concatenating it by few bits which specify the exact type, okay? And this type is later used by various modules within the processor in order to know exactly what to do, okay? Now, same goes for y. And now things start to diverge a bit. So let's start with the CPython side. So it says resolve plus. So what resolve plus actually means is that this is the first time that we have enough information in order to know what kind of operation we're expected to do here. Because adding two integers together is not like concatenating two strings together, right? So we need to take a look of the types of the operands that we operate upon and find the corresponding function, the corresponding plus function. We then need to unbox. Unbox means that we need to reach out to the objects which reside on the heap and pull out the values out of them. And then we can invoke the function. Then we can create a new object that would represent the box of the result. We need to push in the result into it. We need to pop out the operands from the top of the stack and push the result back into the stack. Now, remember that all of these steps are being done by the virtual machine. This is all software, okay? So if you see the translation to the corresponding assembly of x86 or ARM, this is absolutely long. And on the right-hand side, we can see that PyXL says here, add two values in top of stack. So what does it mean and how does it do so? Okay, so we know that in a binary operation, we always address the top two most items on the stack, right? So since we're working in hardware, I can just connect physical wires from the stack module to the ALU. ALU stands for arithmetical logical unit. This is the part in processors that does arithmetics, okay? And weirdly enough, in this case, it also does string concatenation, but whatever. Okay, so it adds up both terms together, and then it just pops out the values and pushes in back the result from the ALU to the top of the stack. And that's it, we have a result now, okay? Now, when I started working on this project, as I said before, I was thinking about it from the perspective of someone who wanted to do classical machine learning feature generation and wanted it to go fast. Or in general, I just wanted to make Python go fast. So I started working on this project, and once things started working out, I had this realization that what I actually got here was simple because, it was just me and not thousands of employees refining an architectures for decades. And because it was simple, it was also low powered, okay? It doesn't require much power to run. And it is deterministic. And deterministic in the way that if you plug in the same input to the same program, it will always take the same number of cycles to execute, okay? So this actually means that this is a natural fit for embedded and real-time systems, okay? Places where Python, maybe a bit in MicroPython for embedded, but for real-time, Python was not a player there in that field. So with this realization, I understood that I needed to start comparing apples to apples. So I bought a PyBoard. So what's a PyBoard? PyBoard, it's a board, and it has an ARM M4 processor on it. Okay, not to be confused with the Apple M4. This is a totally different beast. This is for low power embedded kind of things. Okay, and it runs at 168 megahertz, and it runs MicroPython. MicroPython, the ones of you who don't know, is like C Python, which means it's a virtual machine, but it is meant to run on constrained embedded systems. Okay. All right, so you remember the Fibonacci function from earlier, right? So let's see how it stacks up now against a PyBoard with MicroPython. So these are the results of the PyBoard, and this is PyXL. So now PyXL is 50 times more efficient than the PyBoard. And if I just wanted to talk in terms of speed, because PyXL currently runs at 100 megahertz, it's already 30 times faster, okay, in real time measurements. Okay, so let me show you how it will works. Okay, so I have a video recording of me running PyXL on my computer, this Fibonacci benchmark. So let's see how it goes. Okay, so this is just a regular Fibonacci function. And at first stage, I'd like to show that it works with just regular Python. Now I'm compiling it for PyXL with the PyXL compiler. And I'm sending it off to the board that I have that has the PyXL chip on it. And the IP address, as I said before, it talks to it via network. So this is the IP address, and the a.out is the binary file. It loads the program onto the board, it runs the program, and then we have our result. Okay, so as you can see, the result is 610, and the number of cycles is exactly 37,201. It will always be the same number of cycles. Okay, so current implementation. So what does it actually work on? Because it's not like I went to a factory and told them to start making PyXL chips for me. I don't have that kind of money. So I'm using this. This is an RTZ7 board, and there's not much interesting going on here except for the big black thing right in the middle, okay? So this is a chip called Zinc by a company called Xilinx, which is a part of AMD today. And this is a two-part chip. One part of it has an ARM core, which I am using as the control CPU I have shown earlier, okay? And the other part is an FPGA. FPGA stands for Field Programmable Gate Array. And it is a kind of hardware that is used for prototyping of other types of hardware, among other things, okay? So I'm using this kind of thing to prototype. It's really easy to prototype with an FPGA because you don't have to go to a factory each time you connect something new. And it currently works at 100 megahertz, and it has to do with FPGA kind of limitations. But keep in mind that this is not the end game, okay? This is just for development phase. Moving forward, this could be taped out to an ASIC and be a really cheap chip, okay? So a few use cases that I have thought that could be compelling. So edge and IoT, such as home automation. FPGA software. So an FPGA software means that you take a CPU design and you place it on top of an FPGA. This is usually used for configuration and orchestration of hardware in general. And if you think about it, PyXL is already kind of is that, okay? Real-time and embedded systems, industrial settings, robotics, okay? All kinds of places that you had to write real low-level C until now. And I think the most compelling one is the HML machine learning inference or AI inference, because there's this thing called TinyML, which is kind of a bunch of guidelines of how to run really small, low-powered machine learning algorithms on edge devices which runs on batteries. So this could be like an end-to-end solution where you can write everything from configuration to business logic to the model itself, everything in Python. Okay, all can be in one language, and you can work really fast like so. So in conclusion, what we have today is our first processor that is built from the ground up just for Python. It unlocks new use cases for us because Python was not in the game of real-time and embedded, at least not in a serious capacity. There's no need to rewrite things in C after prototyping. And what I'm trying to achieve with this project is that you do not need to jump through hoops to make it go fast, okay? You do not need to resort to assembly, even though you could. The main thing to remember here is that I'm trying that you write Python like you would on your computer, and most of the time, at least, it should not surprise you, okay? You should get good performance, and the platform will take care of you. So maybe in the future we can stop rewriting in C and just ship Python. Thank you. So I have this website. I don't know how many of you have already seen it. I understand that many of you already have because there was this really explosive post on Hacker News. But if you want to see some cool demo, or you want to be updated on this project, or you want to ask questions, or you want to collaborate, whatever, please sign in and leave your details there. I will not spam you, I promise. Okay, so thank you very much. I don't think we have much time, so I'll answer any questions that you may have right outside in the hallway. So thank you again for coming here today. It was a pleasure.